Welcome back. Today we start Chapter 8, Multiplication. Like the other sections, we will look at several parts, the models, properties, algorithms, and mental math. But today we focus on models. What are the different contexts in which multiplication makes sense? There are 6 different models we'll look at, and the first is the most basic, joining equal groups. Let's say I have 4 pennies in a group, and then there are 3 groups of those 4 pennies. We might express this as 3 times 4. Think about the language. 3 times 4. I have a group of 4 being repeated 3 times. Now, of course, you might also think of this as 4 times 3, and that's okay too. What might be another example of joining equal groups? Maybe, let's say there are 5 taxis, and each taxi holds 3 people. How many people are there altogether? So this would be a joining equal groups problem where 5 times 3 is the appropriate calculation. Next one, rectangular array. Sometimes we have our objects not just in groups but very orderly, like a chessboard is 8 squares by 8 squares, and so I can figure the total number of squares altogether is 64. I have a picture of a boy on a bench. There are 4 pictures along by 3 pictures high, so there's 12 pictures altogether. Rectangular array is really very similar to the joining equal groups. If I have 3, 4, 5, basically like a group of 5, and then that group of 5 is repeated 3 times, you can think of this as joining equal groups, but since it has this nice structure, we can also think of it as a rectangular array. Here's our problem. Let's say that there's a stage and chairs are set up in front of the stage, and every row has 5 chairs and there are 3 rows. How many chairs are there? Here's another example where the rectangular array model is appropriate, and 3 times 5 gives us our answer. Very abstractly, we can think of multiplication as simply repeated addition. If I add 3 to itself, 3 plus 3, this is 2 times 3. Or if I add a lot more of those, 3 plus 3 plus 3 plus 3 plus 3, I have 5 of those, and this gives me 5 times 3. Moving on. Joining segments of equal length. Now I'm moving into the realm of the continuous. With joining equal groups, I had discrete objects that I was holding and counting one by one. But a generalization to the continuous brings us joining segments of equal length. So I have a length of 4. It's not like 4 objects, it's a length of 4. And that's repeated 3 times to give me a total length of 12. We can group the number line into this system also. If I jump on the number line in segments of length 2, we end up with a total amount. So we might call this 5 times 2. And the total length I achieve is a length of 10. Maybe, let's say you go on a 10K race. Here's another problem. And you do a 10K race, and then you do that 7 days in a row. What's the total length that you run? We might think 10K, there's day 1, day 2, day 3, day 4, day 5, day 6, day 7. So 10K each time, so 7 times 10, 70. So 70 kilometers was the total length that was run. Area. Area to me is maybe the most fascinating multiplication model. It is the generalization of the rectangular array into discrete. And rectangular array is very easy to believe that multiplication is appropriate. But what about a situation like this, where there's a rug that is 1.7 meters long and 1.3 meters wide? Why is it that multiplication is the appropriate operation? And it seems like it ought to be, but it's not really like I have 1.7 things and I multiply by 1.3 things. So there is an abstraction going on here. Take a look at the picture on the right. This is a great way of showing the multiplication of fractions. In fact, let me draw a picture up on top. Imagine we have a 1 by 1 square. This 1 by 1 square, and I'll divide it equally in half that way. and I'll divide it equally into thirds in the other direction. So since the square is 1 by 1, very clearly its area is 1, and so each little square, or each little rectangle inside, has area 1/6. Well, what was the length? Along the bottom, the total length was 1, so this length is 1/3. And the height, well, the total height was 1, so this height is 1/2. And so my area model tells me that 1/2 times 1/3 equals 1/6. In the picture down below, they do something even more. They say 7/3, so that's the length going across is my 7/3 wide, and then 5/2 is the height going up. And you can see that the orange parts are all sixths, and so you could literally count all those sixths in there and discover that you have 35/6. Now, when we get to algorithms, we'll see that to multiply fractions, you just multiply the tops and you multiply the bottoms. But that algorithm completely hides the meaning of what's going on, and I really like a picture like this to explain multiplication of fractions. It uses the area model. Okay, our last model is the tree diagram. Often we're expressed with choices or combinations, and in the situations where I have choices or combinations, that's when a tree diagram is often useful. Suppose you go to the ice cream store and you have 2 choices of cone and you have 4 choices of flavor. So by drawing a choice for the cone, and then from each cone I draw my 4 flavors, notice that these are repeated, you can see you end up with 8, 1, 2, 3, 4, 5, 6, 7, 8, 8 possible ways to make your ice cream cone at this store. So 2 times 4 equals 8 gives us the solution we seek. So that's it. Those are our multiplication models. Try the worksheet, think about those problems, and ask me as you have questions.